Welcome back, everyone. My name is Bjarne Børresen. I'm the VP leader for the work package number 6, Communication, Dissemination and Exploitation. And I was supposed to be the chairing this meeting, but I had a double booking this morning, but okay, I'll take over from now. So welcoming you back again, and I'm happy to give the word to Urban Lundin, who's going to present some of the works from Work Package 4.
Thank you very much. I think this microphone is on, very good. So as you heard, my name is Urban Lundin, and I really have to acknowledge the work of my teammates in this work package. So now we move on the shaft. We are from the bubble machine up to the shaft onto the electrical aspects of a hydropower plant. So I've called this overcoming electrical challenges. You might think, are there any electrical challenges with hydropower these days? And I think we have tweaked the electrical machine and also the power system a little bit. So the team, you see here, the team members, and I'll introduce snippets of results from all of these team members. They've done a great job, and it's been a pleasure to work, and I'm amazed of what they have achieved actually. But just for you guys online as well, what are we talking about? What does a flexible generator mean, a flexible powerhouse layout? Well, it means that we have a highly efficient generator, maybe with a full power converter in order to be able to use variable speed that supports the electrical grid. So we might say that we are talking about shorter time aspects and more stability things than just a long-term perspective. So how do you achieve this? How do you achieve a highly efficient generator with a full power converter and so on? Well, we need to look both in the internal layouts of the power plants. We have to look on the generators themselves. And then, of course, the converters, which is one of the main components that has to be developed for these high powers that we're talking about. So we have to say that there are several areas that needs to be addressed. It's not only the converter, it's not only the generator, but we have to look on several things at the same time or simultaneously. So this is a figure which what we are talking about. We have the transmission system on the right here. We would have a transformer typically. We will have the converter, and that's not a standard component for the powers that we're talking about, hundreds of megawatts. Then we have a generator, and these generators, they could be purpose-built for variable speed, or typically we might reuse our old generators. And the question is, if we reuse an old generator, how does that live with a power converter? And then we have the other systems there as well, the turbine that you see. Then the question is also how to control this machine. So you have this man with binoculars looking into the grid and saying, okay, what does the grid need, and how do we want to control our machine in order to support the grid? So just to place people in different boxes here, we have University of Strathclyde looking at the ancillary services and the grid's need on this overall controller structure. For the converter, we have Chalmers and NTNU. We've been looking into both the design of the converter and the control of the converter, machine side control. And then inside the generator, there's been Uppsala University, NTNU to some degree, and SINTEF looking at design aspects of the generator, but also the installation. Because when you put one of these converters, what you do is that you basically chop up the voltages that the generator sees, and that can have an impact on the installation levels in the generator. So let's start with some results, or just a snippet of a result from the ancillary services. This is a model of a hydropower plant. So you have a reservoir, you have penstock, surge tank, and so on. And of course, what you can do is limited very much by the waterways, the surges in the system, and so on. So you have a synchronous generator with a converter, and the question is how much can you push the generator, or how fast can you operate it so you don't cause any trouble inside the waterways as well. So you would start with models like these. Models including the control, the governor, or the governor structure of the overarching governor of the converter. So they would go into this box, the converter here, the control for the converter. And then you can compare a behavior, for instance. How can you sort of improve then the behavior? Well, here's a simulated frequency drop, and then if the frequency drops, then you want the power to come online very quickly. Now, a conventional fixed speed might behave according to the red curve that you see in the bottom graph. So you have a slow uptake of power, which means that you'll have a loss of power during this outtake. But if you have a frequency converter that you can play with a bit more with the speed, you can borrow energy from the rotating mass and eject that as active power on the grid. And then you have to simultaneously control the guide vanes. So you have sort of two power controllers, you can say. The guide vanes and also the power converter itself becomes the controlling aspects. And then you see that behaves much quicker. But of course you have to behave quick in a fashion so you don't create problems for these waterways. And that has been the challenge that the University of Strathclyde has worked on for quite some time. And yeah, more results of that we can see in the publication from them. So let's go into the frequency converter from Chalmers and NTNU. So the control of them and also the design of multi-megawatt converters. This is a busy slide, but it's quite a nice setup where instead of having you don't see a turbine here, but you see an induction machine that can be operated as a turbine, controlled as a turbine. You can even implement the waterways and behavior of the power plant in that control. So that's the green machine on the left. And then the machine on the right here, that's the synchronous generator, which previously was directly connected to the grid, but now there's a converter there as well. So when you have a setup like this, you can basically do a lot. You can play a lot with it. You have more control because you have this converter, and you can control the turbine in different modes. So, for instance, you can speed control. You can operate on the DC voltage level in the intermediate stage between the back-to-back converter. But also interesting to see how can they go from pumping mode to generating mode, or from generating mode to pumping mode. So here's one example of such a switch. So it goes from pump to turbine mode, and if you look on the bottom graph, you see a blue line saying -1 to +1. So that's basically reversing. You stop close the inlet, you stop the machine rotating, and you want to rotate it in the backwards direction, and then you have it running in that speed, and then you start to load the machine. And the interesting bit here is looking at the time scale here. So within matters of seconds, or at least minutes, you can go from full pumping to full generation. And the question is then, how do you implement the controller? How do you make sure that this doesn't cause any problems again for the waterways? That can be quite a challenge. This, of course, relates to the high ramping rates that Hydroflex was covering. You want to be able to go from pumping to generating very fast. And with variable speed and full power converters, then you can really make this transition much faster. A conventional shift, if you just have a directly connected synchronous generator, you would need, I don't know, maybe 4 or 5 times at least this time, maybe 10 times this switching time that you can obtain with a full power converter. So I think we have a good setup that can also be used for looking into future projects on this aspect. So that's an NTNU machine. What about Chalmers? Well, they looked on the actual design of the converter itself. And this is a very simple converter, you can say. It's a 2-level converter. So you basically have you would have another converter on the other sides from AC, and then you have a DC stage, and then you have AC here as well. And this will then feed the motor, in this case, or the generator, with voltage. You control the voltage will control the current and the power. With this type of converter, the current can look like this. We'd like to have something which is very sinusoidal, very neat. And of course, when you look at these curves, they don't look very sinusoidal. So one thing that we'll come back to when we talk about the installation is the question is, how does the machine react when it sees these types of currents? So these types of current will then have an effect inside the generator/motor. But this is the simplest converter you can make. So are there other topologies? and this is then being investigated at Chalmers. So here you have a multi-level, instead of just 2 levels that you switch between, you have several levels, and then you get currents which are much nicer looking like this. And of course this is something which the machine will like to a much larger degree. The price you pay, if you look on the top left or bottom left, you see that you have many more of these electronic switches. So you'll have more switches, and then the question is, well, are they reliable enough? What's the losses? Because there's a loss inherent in each of these switches. So that has been another aspect of this HydroFlex project, to look at the losses inside the switches, both from the switch and the conducting losses inside the switches. And just to show one aspect, here you have a few topologies, the bottom here, MPCA, MMC and so on, and 2 level on the left there. So the 2 level is the one where I showed on previous slide, and then I think it was the 5 level on the previous slide, but they have investigated up to 9 levels and seen, okay, what efficiency can you typically expect from a machine then? Now we're talking hundreds of megawatts, so losses are important. So you see for the 2 level on the far left, 1.56% losses, and of course 100 megawatts, that means 1.5 megawatt of losses inside the converter. But then if you move on to this multi-level, then you will have losses which are below 1%. So it is possible to design a converter with losses less than 1% of power. And of course, this multi-level, they are the preferred option. So the next parts have been looking into the generator, looking into the installation, and also what happens, how can we design a machine which is more suitable for this converter-driven generation. So what about the installation system? Well, the focus has been on the stress grading tape. What you see here is the green. So what you see here is the stator bars coming out of the stator core, and they have different types of installation levels when it exits the stator core. And the different types of installation, they are there for different reasons, you can say. Of course, you think you just have to make sure that you don't have short circuit between the high voltage and the stator core. But also you have to care about the voltage profile, how the voltage or the equipotential areas, how they sort of leak out through the stress grading tape. So you can see different types of stress grading tapes here. You see equipotential lines, and you have pros and cons of different types of stress grading tapes. What happens if you don't take care of this? Well, here you see something painted red, and the things painted red, that's the bars coming out of the stator core on the left. And then you see this little white ring around the conductors. And that's small electrical discharges which are sort of eaten away on the insulation. You see there's sort of a black tint also inside there, and that would be part of the stress grading tape. So depending how you design it, you can induce this problem, or you can make it worse or make it better. As always, this is a trade-off between different engineering targets that you like to have. You'd like to have something which can cope with the voltages, doesn't matter. But then if you make something which is very good for field, then you pay a higher price on the temperature side, the thermal side. And we don't want to have too high temperature in the insulation, because that breaks down the insulation. So the work at SINTEF has been addressing these issues. Maybe I just take out these. So if you look on the surface temperature, when you have this stress grading tape, now you see on the bottom on the x-axis, you see frequency here. And normally, I mean, we work with 50 Hertz frequency. We think that's a grid frequency. But for a converter, then the converter will switch maybe kilohertz, maybe several kilohertz. So that's why you have the frequency range here on the bottom axis. And then we changed the conductivity of this stress grading tape, the SGT, which is indicated there. And you can see that if you have low conductivity, you get the blue one, then you get the lowest temperature. That seems very good, because low temperature, then the thermal insulation sort of keeps, it doesn't degrade so quickly. High conductivity and high temperature is not so good. But then if you do have low conductivity, you pay a price with the electrical field. So you see that the blue the best case in temperature becomes sort of the highest field stress around the material. So you have higher field strength, and then you have more likelihood of having these discharges, the corona discharges. So for the field, the best case is the high conductivity tape. So again, sort of a engineering compromise between two aspects that you have to care about. And also, we can see that the frequency, well, what about the x-axis here, the switching frequency? We can see that it already at very low frequency, we have to care about these properties. So what's the best case scenario? Well, it really depends on the converter design, the voltage levels and so on. So it's not possible to say that this is how it should look like for all cases. So then we think, well, what can we then do about the generator? Are there any design changes that should be done or can be done on generator in order to make it more suitable for converter-driven operation? So we have worked on this at Uppsala University, and our idea was in order to reduce the losses and make sure that we have a machine which can then support the grid with more better sort of damping qualities. We remove the damper bars, and that's sort of a contradiction. We want more damping, so therefore we remove the damper bars. Well, then we have to replace them with something else. So this requires us to do something novel on the magnetization system. So our rotor, which we have developed, looked like this. It's sort of you can say it's a fully laminated rotor, but there are special, you see in the middle section here, there's a thicker bar. So it has some aspects also with damping, depending on especially when the startup and the different frequencies. So the plan is that this experimental part would then look like what we have on the left there when it's fully manufactured. But this has to go together with power electronics. To control the currents in the field winding, or the field voltage, then we have to have faster control. And power electronics is the enabler of operating the field current in a more faster manner and achieving more. So we have to sort of, the passive thing that we remove, the damper bars, then we replace with an active component in this magnetization system. So what we're working with is these power electronic switches that you see here on the right. This is operated, this is pre-testing, you can say. The idea is that these components will actually be sitting on the shaft and rotating. They'll be very close to the rotor poles themselves. And then, of course, we have challenges with communication, challenges with these components. For instance, the black thing you see is a capacitor, and we have to use solid-state capacitors. We can't use electrolytic capacitors if it's spinning with high G-forces and so on. So there are challenges in both the design of the system, but also components. They have to be able to withstand very high G-forces. So an example of when this can be useful, well, this is just a simulation work because we haven't done the experimental work yet. But if we look on the damping properties, so I said we're going to remove the damper bars and passive system, replace them with an active system. So how good is the passive system? Well, here you see a simulation using this model, and at 10 seconds you have a step in the torque, and then the torque out from the generator will then find a new equilibrium. And you see it's a damped sinusoidal, so this damping comes from the damper bars. You know, these currents in the rotor, and the rotors will sort of damp the difference in speed between the grid and the actual rotor. So the question is then, can we achieve the same damping with an active system instead? So this is what we've done, and this is the damping we can achieve with an active system. So you do see transient, you do see some oscillations, but you can see that the damping is much larger with active control than it actually is with passive control. You could actually dimension the passive control to be faster as well, but that comes at the cost also. What do we do here? Well, it's the field voltage that we control. So here you see how the field voltage should be controlled during this transient. So that gives you sort of an overview of some of the results that's come out of the Hydroflex project. So if we were to answer this question, has the Hydroflex project made generators more flexible? what can you say? Well, I think the modeling for control and also the voltage dips, the low voltage right through that has been simulated at the University of Strathclyde. We've seen that we can achieve better performance with the full power converter and better control there. Models developed and also the trade-offs are not so big and the benefits are there for sure. We have built this test bench, an amazing test bench for pumping generating, been developed and verified, and I'm sure that's going to be used also in the future for more experiments and more research on this. Different topologies of converters have been investigated, and good, you all woke up, right? Was that your PhD student? It was the converter, yes. We have planned to show it here, but it was a mishap in the lab. So different topologies have been investigated. Of course, these are not manufactured yet, but I think if we push the power ratings up to hundreds of megawatts, I think some of these topologies will have to be used. And what about the generator side? Well, this rotor concept has been developed and partly tested. We're looking forward to do a bit more testing, hopefully within the time span of the Hydroflex project, if we get our components from suppliers. But we have a design which will have a better, it will have better capabilities of being converter driven. And also, not the least, the insulation system has been investigated, and a way forward has been sort of shown, a way forward has been shown how to improve it. And lastly, I just want to thank the team. This is the people that's been involved in the Hydroflex project. And then we have the overarching of our old heroes from the 18th and 19th century, well, the 19th and 20th century, that has been guiding us for this dark patch. Okay. Thank you very much for your attention.
Thank you very much, Urban. Are there any questions from the audience? Arne?
You have this special design of your rotor without any damper bars. How do you protect your field winding in case of a short circuit?
Yes, that's of course. I mean, it's not only damping that the damper winding does; it's also protection against also negative sequence currents and so on. But the thing is that we have to sort of integrate that into the converter, or the converter for the rotor. So, I mean, one way would be to maybe short circuit the field winding during such events. So you need very fast control, and you need to also make sure that you take the appropriate measures. And one challenge can be if you have multiple faults at the same time. How do you protect it in that case? Because some of these protection measures might be contradicting each other. So we are still not 100% there yet, I have to say, but I think we have scenarios for short circuits as well.
Urban, do you have any idea of how taking this to the next level, next step? I mean, the hydropower industry is not known to be front runners when it comes to new technology. We want to test and run well-proven equipment.
Well, I think the next step will be to do a pilot, a small-scale pilot somewhere, where you incorporate some, maybe not all of these design changes, but some of these design changes. I know there is at least one power plant in the Alps where they have a 100 megawatt converter already, and that has been operated for many years now. So I think lessons learned from that, but also trying to incorporate so many new topologies in a pilot would be sort of the next stage. As a researcher, of course, you want to say that, well, we've shown a few things, we've asked a few questions, so more research is needed. But also, I think the industry has to realize, well, if they want to see this, we have to take it to the pilot stage. And then, of course, there has to be a business case for doing so. So that's, we are focused quite a lot on the technology, but the business case, yes, that has to be also there, of course.
I mean, it's on a similar note, or first, I guess, also in the X-Flex Hydro project, they are actually going to build some, or maybe I've already installed some pilots on this as well. But my question is, how much synergy is there between what we are doing within hydropower and within other fields of renewable, for instance? I mean, there's a lot of work done on converters for large solar farms, for instance. Is that similar technology, or is there any synergies between the fields?
Absolutely. I mean, I have to say that the birth of power electronics has been one of the biggest achievements in the last 40, 50 years when it comes to electricity, and that means that we have a new tool that we can use in different ways. So it opens up a way to think differently and a way to solve things differently. But a converter for a wind generator and converter for a hydropower generator, very similar nature. And they are increasing in size, so I think we will benefit from that development, and hopefully they will also develop or benefit from, for instance, our development on the installation system and on maybe on the rotor design.
And this multi-level converters that you presented really briefly, how far are they from, let's say, commercial operation? Or
well, maybe we should ask Torbjörn about that.
Okay, so we can say that MMC topology is already used in HVDC transmissions. So it's and it has and the other MPC variant for lower number of levels is already also used in motor drives. I don't know how far it has come with MMC for motor drives. Do you know that, Roy?
Yeah, it is some challenges with MMC for motor drives. It is some challenges with MMC for motor drives because it's so low frequency, so the topology is it's quite costly. But you can achieve, for instance, in such a system like this, 40% of rated torque around 0 speed without derating it. That means you can design it for rated operation, rated frequency, but then you have to derate it approximately to 40% if you should be able to 40% torque at 0 speed. But it's not maybe not. So you have to do some let's say reduction there. If not, it will be too costly.
So the answer is no showstoppers.
And that is was what we also showed in the case where we went from pump operation to generation and so on in the slides here. It's in that cases we have done it with rated torque, but I think that we have to, let's say, close the gate lines a bit, and so you have a bit less torque requirements when you are passing 0, because then you can use MMC, for instance. Yeah, okay.
No, it does. Sorry.
One extra comment just is also when it looks like it's a huge amount of power semiconductors, but the kind of total voltage times current rating is fairly similar, but still it costs more with the drivers for if you have more power semiconductors. So cost is, of course, a little bit of an issue. But I think no showstopper.
And also, if just to correct me if I'm wrong here, but I mean, I understand these questions regarding the isolation, but in principle, I can take my standard hydropower plants from the 70s and refurbish it with this fully converted solution, and suddenly have a brand new hyper-flexible power plant, in principle.
It is possible. I mean, what you can do is that you can also put filters there in between, so you don't see this ripple. But I don't know. Maybe our friends in the Alps. Maybe you know anything about this 100 megawatt, because I think that was a conventional an old generator which was used. It wasn't.
I think you are referring to Grimson.
Yes, exactly, Grimson.
So the Grimson Hydropower, where you have a 100 megawatt converter. We did not have, let's say, this test case within our project, so we did not put our hands directly on the development of these units. But we are working on a smaller case, so it's a 5 megawatt reversible pump turbines, where we are installing a full-size frequency converter. And for us, the main challenge is to understand how to have, let's say, the best profit of this technology when we start up and stop the machine. And I think this is quite in line also with the work that we have been seeing. But we use a standard frequency converter, so the one that you can find in markets.
And the generator is the same which was there. You haven't replaced the generator. But it does require coordinated action between the turbine governor and the frequency and the control of the full power converter. So it is a challenge.
Just a comment on Grimson. In Grimson, it's a retrofit installation, and we have a power transformer between the converter and the original generator. So we are avoiding these insulation problems. But I think that the Indar is installing 2 units in Spain now, and those are 50 megawatt each. And I think those are using this NPC technology directly connected to the generator.
So yeah, development is going in that direction.
The losses you presented, are those just half the transformer? So you have to transform it once?
You mean the losses in the converters?
Yeah.
In the switches?
Yeah.
So let's see here. I think this is from the DC link to the, yes, so it will be, yeah.
Okay. And are these just theoretical values, or are these close to real values?
They are theoretical values, but if you look on the left side, then those have been a little bit verified on other setups.
Okay, okay.
I can just comment on the different topologies, a bit about this DVDT and the insulation issue. I think that the point is that the voltage is not sinusoidal into the motor, it is square waves, but in reality not completely square. It is a small DVDT on the edges and so on. And on this order, the more steps you do compared to if you think you have a total DC link voltage, the more steps you have in a converter, for instance MMC, the smaller each of these steps are. So the DVDT can be less. So it's better for the insulation if you go for a MMC rather than a 2-level. In that case, because you want, it's a limitation, you want to have some speed on the DVDT because that gives switching losses in the transistors. But if you then instead let's say have a smaller step, then you can still have the same DVDT and get a bit less losses in the individual device. So the conclusion is that MMC is better with respect to DVDT and becomes more a sinusoidal, looks more like a sinusoidal voltage for the motor.
At the best efficiency point, when the turbine operates, perhaps these power electronics needs to be bypassed.
That's definitely an option. I don't know, maybe here I didn't show it, but you could actually bypass the frequency converter altogether if you want to operate it continuously for a very long time. Absolutely. But then the best efficient point has to be at something which is synchronous speed of the generator.
Yes, so no, that's not a problem at all, right?
No.
To bypass.
No, to bypass is, I mean, it's a breaker that you have to install, and there are known technology.
Thank you.
Maybe one can say one thing, that then you have to make the design so it suits for 50 hertz. If you skip that possibility, you could perhaps design it for 20 hertz or something. So I think it's not dead for sure that it's a good idea.
Now, like
or the best idea.
Now, like we've talked about, to make a sort of a ridge in the hill chart as well, so you can then the variable speed that really comes to its merit. I mean, and like today there are variable speed units in the world, but now with doubly fed induction, and then you can do a speed variation of 10%. The full power converter allows much larger span. So. But of course, then it comes back to the turbine design. We have to have also benefits from the turbine design. Otherwise, why would you put the converter there?
Just a comment to this frequency. If you only have a converter between the grid and your generator, you do not need to design it for 50 hertz. You could choose everything. I had a PhD student investigating this, and it's not so much to gain then. It's a little bit, but then your machine may be unstable in the power system if you really want to put it directly. We also did this in ABB some years ago for 3 gorges. But the student from my PhD student was that maybe something between 42 to 48 hertz is a very good. So I think our predecessors, they were quite smart selecting 50 hertz. It's a quite good choice.
I noted for wind generators, but there we have to have the gear. And there it seems like the frequency can up at much lower than 50 hertz.
I've heard about hydropower plants operating at below 30 hertz.
Okay.
For extremely weak power systems with just very few units and the load varying a lot. But they cope.
I just have a comment about this. With, of course, if you can operate it at best efficiency point, I think it's a good idea to bypass it if it is a classical machine. Another thing we just should mention that a frequency converter have a PWM pattern at the output, and that can give additional losses in the generator as well, especially in the I believe especially in the damper windings. At least my experience from induction motors, a lot of additional losses due to the frequency converter. So sometimes they put what they call a sine filter, sinusoidal filter, LC filter, at the output of the converters to avoid too much losses in the retrofit application. That means machines which are not designed for frequency feeding.
That's one of the reasons why our initial ambition was to remove the damper bars, because we will have a converter on the stator, but we also have sort of a converter on the rotor, so we feed a high voltage transients also from the rotor winding. So then of course it makes sense to remove the damper bars.
Thank you very much, Urban. It's very interesting results that's been coming out from this work package, and I think it's pointing at some really interesting development in the future for hydropower. We will take one more presentation before we break. So I'll invite Stefan Lundström from Luleå. Yes.